In this video, we're going to learn how the Terranova actually works. Now remember those two things that we need for magnetic resonance. We need a homogeneous static magnetic field. And we need, of course, an oscillating transverse magnetic field. A field that oscillates exactly in resonance with alarm or precession of the atomic nuclei. Why does that static field have to be homogeneous? Well, I'll leave that as something for you to think about. But it has to do with the sharpness of the resonance, the degree of resolution that's possible with nuclear magnetic resonance. So let's come back to our static field. To get a homogeneous field is actually quite an expensive thing. In fact, that's what you pay a lot of money for when you buy a superconducting magnet for a hospital MRI system. But nature actually provides us with a homogeneous static magnetic field for free. And that's the Earth's magnetic field. And here in this room, it's more or less vertical. And I can demonstrate that with this little gimbal mounted magnet here. You can see it's more or less pointing in the vertical direction here in Wellington, New Zealand. There is a downside, however, to this Earth's magnetic field. It's very weak, around about 60 microteslas here in Wellington, New Zealand. And that leads to alarm or precession frequency for atomic nuclei of hydrogen of around about 2.5 kilohertz. And that low frequency leads to a rather weak Faraday induction when we're detecting the nuclear precession signal. The second problem with a weak magnetic field is that we're starting off with a very low magnetization when our spins are in thermal equilibrium. Of course, one way to compensate that is to have lots and lots of nuclear spins, and that means to have a bigger sample as we can, and we do. We have a nice large sample. The other way to compensate is to use a trick, something called a pre-polarizing field, and I'll tell you about that in a moment. Coming back to that oscillating transverse magnetic field, that's produced inside the probe of the Terranova apparatus. And the probe is really the heart of the instrument. It's driven through a cable from the spectrometer, which is in turn controlled by the computer. In fact, the Terranova probe is a bit like a Russian doll. It's got a whole lot of layers of coils inside it. And in order to show you that, we've got over here a disassembled probe where I can pull out the components very easily. At the very centre of the probe is this coil here. It's a solenoidal coil. It's wound with very fine wire. There's lots of turns, well over 1,000. And this is the coil we use to produce that oscillating transverse magnetic field, to disturb the nuclear spins from equilibrium in the nuclear magnetic resonance phenomenon. But the same coil can also be used to detect the signal in nuclear magnetic resonance. Imagine we have the nuclear magnetization processing around in the plane of this coil. Then, of course, by Faraday induction, we'll pick up a signal in this coil, and that signal will be an oscillating voltage. And we can measure that oscillating voltage to obtain the information provided in the signal from nuclear magnetic resonance. A coil like this, a transmitter-receiver coil, really lies at the heart of all nuclear magnetic resonance and MRI systems. The next coil I want to look at is this one here on the outside. This is a coil that is used to produce a large magnetic field just before we start the nuclear magnetic resonance experiment. The idea of that is to increase the nuclear spin polarization in order to make the signal more visible. In fact, if we started off with just the Earth's magnetic field magnetization, we'd have such a small signal it would be barely detectable. This coil here produces a field that's 350 times larger than the Earth's magnetic field. And as a consequence, the magnetization is 350 times larger. And that makes the signal really visible. What we do with this coil, which is called a pre-polarizing coil, or a polarizing coil, is to run some current through it for a period of about 5 seconds before we actually start the nuclear magnetic resonance experiment. That produces a large magnetization so that once we turn off this current, we've got a sufficient magnetization to get a strong signal in our nuclear magnetic resonance or MRI experiment. But there's another coil here, and that's this one. This is a very complicated looking coil. It's got lots of layers and it's got some very ingenious patterns in the windings. What this coil does is to produce a magnetic field that varies in 3 orthogonal directions. And these varying fields are known as magnetic field gradients. And they have 2 particular uses. The first of these is that by applying a very small current through these coils, we can correct for imperfections in the Earth's magnetic field. Imperfections that might occur in a room like this because of perhaps a metallic leg on a table or some reinforcing steel in the wall. And so by adjusting small current through these coils, we can improve the homogeneity of the Earth's magnetic field to the degree that we require for nuclear magnetic resonance to work really well. But the second use of these coils is that they lie at the heart of magnetic resonance imaging. By varying the magnetic field in 3 orthogonal directions, we can produce a Larmor frequency that depends upon position. And that's the basic principle behind MRI. We'll be looking at that in a later video.